Hello world, I'm Matti and I would like to talk about the version 0.0.9 release. As always, the meat of this message is in a blog post. In this case, it's the 0.0.9 release notes. Barry uses semantic versioning, which means that this petty number supposed to communicate that the implementation is incomplete, unstable, and even more importantly, it lacks any software compatibility guarantees. Which basically means that BSN file loaded into one version not necessarily does exactly the same thing than loaded into another version. Because of this, we provide public access to all prior releases for you to be able to load your BSN files into any version. If we go back to the blog section, we can see that we already have a newer release, namely version 0.0.10, which means that if we press on the play link, that will lead us to the latest release. If I would like to do this demonstration in the exact version that it's about, I only need to change latest at the end of the URL to the version I'm interested in, and that will lead us to the old version. Because I don't want to work around all the bugs already ironed out in the latest version, I will do this demonstration in the newest release nevertheless. So the biggest improvement of version 0.0.9 was a feature called atomic edits. The introduction of atomic edits is an architectural change to the system. It's not really visible from the user's perspective. To make it visible, we will have to use a technique that lets us inspect its behavior. Dagger always parses only a single line at a time. If you press a key to initiate a change, you will always end up having two versions of the tree, one before your edit and one after it. The nice thing about atomic edits that it can detect if only a single idea's value has been changed. On one hand, it saves us a lot of work because we can keep the entire idea tree intact and only swap the value of this single idea. And on the other hand, even more importantly, it can save us a lot of calculations because in Dagger the whole evaluation process is cached, and in these cases we only need to invalidate the evaluation path is leading to this single idea. To demonstrate this new feature, I need a painfully simple example. As usual, let's say a is 1 plus 2 and add the second line with a multiplied by 3. This input will produce this tree. This is an addition, some transparent decorators in it, goes into a list, and this is the second line with the multiplication. And the important part is A is references this label. So this line result depends on the first line results. To demonstrate caching, we need to attach the so-called extern idea to these operations. And what we'll do in practice is that it will output a log line into the console whenever evaluation passes through that idea. So after attaching these external ideas to our operation, we see that both 1 plus 2 evaluated and a multiplied 3 evaluated. What caching means is that if I change the second line, for example, if I add a new digit to a number or even another operator, this line needs to reevaluate, but this first line never appeared again because we don't have to evaluate that. The results of that line is already cached. On the other hand, if I change the first line by adding something to it that leads to the evaluation of both the first line, 1 plus 2 multiplied by 3, and the second line, a multiplied by 30. Now caching was already working in versions before version 0.0.9. With atomic edits, we went even deeper, and to demonstrate that, we will need another example. And this example is the following: 1 plus 2 multiplied by 3 plus 4. This line produces the following tree with two additions under a multiplication. If I attach an external idea to both these subcalculations and changing only one of them in a way that only a value changes, for example, I add a 0 to this 4, making it 40, we can see in the console that only the part 3 plus 40 has been evaluated, and the result of 1 plus 2 came from the cache. If I change this and add a 0 to 1 plus 2 to make it 10 plus 2, we can see that only that part changed. If I introduce a change which needs a reparse, like I add 1 to the end result, that will change the shape of the tree. So in that case, both subcalculations need to be calculated. Maybe it doesn't look like a big thing, especially not with these very primitive calculations. But later, even a small change can cascade over the entire tree and trigger a lot of calculations. So as tight we can keep cache invalidation, the better responsiveness we will get. In addition to this feature, we also added a safeguard for changes that doesn't change anything at all. For example, here I have a list of two additions. This is a list. And if I attach the external operator to both, we see that both needed recalculation. But if I go and add another space between the two, which doesn't really change the shape of the tree, then none of them is reevaluated. So these are atomic edits. It improves system performance, but it also made some features simpler to implement. Namely, we could improve label renaming and reference refactoring. Before atomic edits, we were able to refactor labels across lines. What we wasn't able to do is to refactor references in the same line where the label was in. In this case, A labels 1 and this reference is this. So the reference and the label definition is at the same line, and we can see that the result reflects this. Now, what atomic edits made us possible by catching the single idea value change is when I rename this label, the reference on the same line changing with it. It's also the first case that we need to edit the edit line while we are editing it, because we need to update the string also to reflect these refactors. So this is it for now. This was the demonstration part of the release notes. I will put the link to the blog post in the description, and thank you for watching. See you in the next video. Bye.